Hi, this is Professor David Farina, and in today's lecture we're going to be talking about Chapter 1, the Copernican Revolution. And to start us off, as usual, I just want to take a moment and give you a chance to look at this picture and kind of try to interpret with this one what exactly you're looking at. You can pause the video now. So now that you've had a moment to look at this, I want to highlight just a few things. In the first part, you can see here along the edge of the picture, we have the celestial sphere and kind of the ancient way of looking at the night sky. And you can see that there's a person here, and that person, which, given that this is called the Copernican Revolution, maybe that's Copernicus himself, is poking his head through the celestial sphere, and he's looking into the mechanics, these wheels and these cogs, the mechanics of the heavens, and trying to understand them in a new and different way. So pretty neat little artist's rendition of this time, and I think it's telling for what we're going to be talking about today. Here are the topics of Chapter 1. So, the motions of the planets, the birth of modern astronomy, and I'm going to be adding, by the way, to both of these sections with some other content. The laws of planetary motion and Newton's laws. And also here I'm going to be adding a few things as well. So definitely worth your time to pay attention through these videos because I'm going to add in a lot of good content. And here is some of that content. So I want to give you a background on the roots of where did astronomy come from originally. We have record, mostly through these structures, of people who were studying the heavens back even during the Bronze Age and even the Stone Age, as we'll talk about in a moment. And these monuments have some significance in terms of astronomy, various different purposes. This particular one in Newgrange, Ireland, built 3200 BC. The significance to astronomy here is that during the winter solstice, there is light that is able to shine from the sun directly through its central chamber. And this is something that we've seen also in other places. I would reference you to the caves of Lascaux, which I don't have in my presentation today, which go back way further, thousands and thousands of years before this structure was made. We have evidence that people in France at that time were choosing caves that had very significant astronomical influences as well. So people have been watching the sky for thousands of years. Probably the most popular of these structures is Stonehenge, and here I've got some kind of cool little diagrams of Stonehenge. Now, construction date is not quite unknown here. We have some time between 3000 and 1800 BC. And it's likely that this process was in multiple stages or phases. We see some evidence of this in the actual structure itself. If you look around the edge, there's these ditches that seem to have been dug, as well as these little circles which are indicating post holes, trying to get a basic circle. And the vantage point that you would stand at is, of course, in the center of the circle. And then there are the stones that most people are familiar with around the middle, and the ones that you can see in this picture here and also the picture at the bottom. Those are the ones here in the middle, this kind of U-shaped thing. But what a lot of people don't realize is that these stones out here, called the heel stone, as well as these two stones here, they have a very important astronomical significance. As you can see, it says here in the diagram that most of the summer solstice is going to fall right over that heel stone, which is this right here. So this is their way of kind of telling time, telling the seasons. It also has some ways to determine like the most northerly moonrise and moon rise in the southern parts of the sky at the winter solstice. So there's a lot of calendar and moon related things going on here. So that's the astronomical significance of Stonehenge. I've also watched a video that said there might be some sort of connection to the burial of ancient relatives, and that this was a gathering place at the summer solstice, which is the longest day of the year, as kind of like a celebration, and also at the winter solstice possibly as well. So thoughts on this? I'd be interested to hear your thoughts as well. So there's the summer solstice with the heel stone right there. This one is in the United States. This is in Chaco Canyon, New Mexico, and it's on a butte, and this is called the Sun Dagger. So if you look to the picture on the right, you can see kind of like this bullseye shape, and on specific days of year, the summer solstice, the Sun Dagger, as it's said, which is created by two rocks that are facing towards the sun. They create this dagger effect where the dagger goes right through the center of this bullseye on that particular day. Any other day of the year, and it would be somewhere other than the center of the bullseye. So thought to be, once again, an astronomical significance. This one is a mammoth tusk that was found in Ukraine. And it's possible that these inscriptions are indicating something like a counting of something astronomical, maybe moon phases or something like that. We don't have a lot of information about things prior to the ancient Greeks. It's mostly interpretation. But starting with the ancient Greeks, they wrote things down, and that written word is preserved, and as a result we have a lot of information from the ancient Greeks, and a lot of their mathematics was also preserved. And what a lot of people don't understand is, or don't know I should say, is that the Arabic cultures were preserving the Greek understanding of things after the Europeans went into the Dark Ages. And so if it were not for the ancient Arabs, we would probably have lost a lot of this Greek knowledge as well. So we have a lot to owe ancient Arabic cultures and their preservation of both mathematics and scientific knowledge. Now, we have a few of these very prominent Greek astronomers who had ideas about how our solar system in particular worked. And these ideas, sorry about that, the phone is going off, of course. Sorry about that. These ideas were based upon something called the first principle, so which we'll talk about in a second. Some of these first principles were that the Earth was imperfect and that it was a changeable place. It was obvious to them that the Earth was not something that was a constant. It was always dynamic and always changing. Whereas they thought the heavens, or what we think of as space, was perfect. And there was a lot of things to support this. And that included that things like constellations didn't seem to change very much. And over time, they didn't notice any changes other than the planets in their motions. Each year, the constellations cycle around, and they are the same ones over and over and over again. Excuse me, I'm just going to turn this off quick, so that doesn't happen again. Okay, so these nested spheres were thought to be the way in which the planets moved, and this time they had a geocentric model, or Earth-centered model of the solar system, which we'll talk about a little more here in a moment. So what is a first principle? A first principle is a basic, like a hunch. There was these first principles, that these are things that the ancient Greeks thought were just obvious. And as a result, they didn't question them. And they didn't do any sort of additional experimentation. This was not science. It was more of a philosophy thing. So the geocentric universe was one of them. The perfect heavens was another. And one of the main things to support their idea was that they didn't observe parallax. They understood that if the Earth was going around something else, that we should observe a parallax effect. And we've done something, or will be doing something in class with this. But if you are understanding the idea of parallax, as things move, your perspective moves with it. And the stars, they didn't see this parallax. And so they thought, well, there must be a reason. The Earth must be stationary. Turns out they were wrong. Eratosthenes was another person that was around during this time, or just after this time of the ancient Greeks. He was in Alexandria, Egypt, at the Library of Alexandria, and we'll be doing an activity in class with this, or have done one already. So we'll go into a little bit of detail today. The basic premise is he was able to calculate the Earth's circumference, and therefore the Earth's radius as well, by understanding the angular distance between two locations, and those locations were Syene and Alexandria. And he found that that was a 7-degree slice of what is Earth. He knew the distance between these two places, and through simple multiplication and the knowledge of 360 degrees in one circle, he was able to take a ratio and determine the circumference of the Earth. So the known distance between Alexandria and Syene was about 5,000 stadia. 7 degrees is about 1/50th of the distance between 7 degrees is about 1/50th the distance around the Earth, 360 degrees. And so he took those numbers and he multiplied them together. 50 times 5,000 stadia. And he got approximately 40,000 stadia. Gotta check my math on that. All right, so Hipparchus. Hipparchus placed the Earth away from the center, but he kept the perfect spheres. And so he still was dealing with some of these first principles and didn't completely break the whole thing. And here's why. Is because we did observe kind of like this weird motion of the planets. They appeared to be moving backward against the sky at times. And they couldn't really explain these very well. So they started adding these things in called epicycles. Now, just to be clear, this is not a correct model of the solar system. But in his time, we've got Earth here kind of slightly off from the center. We've got these epicycles that the planets were thought to move along. And he does have the sun on one of these larger rings. Notice it does not have an epicycle. Interesting. And that the Mercury and Venus were connected by what he thought of almost like a rope between the two, and that these epicycles moved along this line. The rest of them had epicycles as well, but they had to go around these bigger things called deferents. And so between these deferents and these epicycles, they were able to, in a very complex way, resolve some of these weird peripheral issues they were seeing when they were monitoring the planets and their motions. Usually when things have to be complex, that means they're probably wrong, which these are. So these are the epicycles. And here's a picture of what these weird motions of the planets looked like. So this is Mars over the course of time, and you'll start over here in the west. It'll be moving like the planets should, and then all of a sudden it'll start reversing itself. And this is what we call retrograde or backward motion. And it's why they thought they needed these epicycles. And this happens over a very short period of time here. You'll see October 3rd to December 12th. And then it starts to move forward again. and then it does another epicycle. And this process of trying to understand these epicycles, or I should say these retrograde motions, was why we added the epicycles in. So there's the Earth slightly off from the center. There's a deferent of Mars. And then there's the retrograde motion, the dotted line. And then here's the epicycle that's used to try to describe it. And that's that epicycle backward through time. If you ever use one of those like scrolling art tools, I'm a loss here of what they're called, but those little scrolling art tools will make this kind of cool pattern as well. So this was like the Ptolemaic system, and up until the Copernican revolution, this was the main way that most people accepted that our solar system worked, and it was mostly unquestioned, except for by Copernicus, which was about a few thousand years. So just some additional information here. The word planet actually means the wanderers. Pretty much everything else in the sky, stars, are all fixed. At least they appear fixed over short human lifespans. But over the course of even just a few days, you can watch the motion of a planet. And so these wanderers were the only things that were thought to move, and also they were worshipped as gods as a result. They also changed their brightness, they changed their speed, they have this retrograde motion. And they're very difficult to describe in this Earth-centered model of the solar system. Some additional planet information here on Venus and Mercury. The inner planets of Venus and Mercury are able to be seen mostly either in the morning at sunrise or in the evening at sunset. Usually they're mistaken as stars, but they are planets. The way to tell is that planets don't twinkle. Stars do, of course, twinkle, like the song says, "Twinkle, twinkle, little star." Planets don't twinkle, and that's because they actually have some width to them. And as the light passes through the atmosphere, the Earth's atmosphere usually causes kind of like a shaking effect. If you've ever been outside on a hot summer day and you see the kind of waviness above the asphalt pavement, that same stuff's happening up in the atmosphere. We call it seeing. But when the light from a star passes through the atmosphere, it moves back and forth, or twinkles. The proper word is scintillate. But as these stars scintillate or move back and forth, that's seen because they're effectively a point source of light. Planets that have some width are able to kind of avoid that effect. At least on the scale that your eyes would see. If you zoom in with a telescope, you would start to see some of that, what we call seeing. Venus is the brightest star, or brightest planet. Of all of them, the only thing brighter than Venus is the full moon and the sun. Every other planet is less bright than Venus. The outer planets, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto, these are called the superior planets. These previous ones, these are the inferior planets. So inferior is on the inner, and outer planets are superior. They generally appear to move eastward, and these are the ones that generally do the retrograde motion that we discussed. These are just some models that are from the textbook that show the same things we've been discussing. So there's some retrograde motion of the planet Jupiter, for instance. I didn't want to pass by a very important figure in astronomy. His name is Tycho Brahe. He lived from 1546 through 1601, and he was crucial in making very high precision measurements without a telescope. This is pre-telescope. And also he discovered what ends up being the first ever discovered supernova by a European. There was another supernova that was discovered by the ancient Chinese as well. And this new star, or supernova, which means new star, was of great interest to Tycho because he was still in that Ptolemaic view of the heavens being perfect. And when he saw this new star added in, that kind of broke his thought process, but he could still never get past the geocentric model. One other additional reason he stuck with his geocentric view is because with this new star, he observed no parallax once again. I'm sorry for getting that cut off at the end. Evidence against these Eratosthenes' belief of the perfect, unchangeable heavens was provided by that supernova. He did come up with yet another model of the solar system, but his model continued to have an Earth-centered model. He was getting closer to what we consider the Copernican model. And if you look to the right here, this picture of his device, it was basically like an enormous protractor. And that is Chapter 1, The Copernican Revolution. Thanks for listening, and hope to see you back for Part 2 of the Copernican Revolution. And that will be on the birth of modern astronomy. Thanks again.